Well, today we are dealing with Chapter 2 on foundations. So this is Chapter 2, and it's the first half that we'll deal with in this video. So there are foundation requirements. We'll deal with the earth materials that we deal with. The materials that we build with we call aggregates. That's gravel and sand, and it can be bigger rock than that too. There are some math and aggregate volume calculations we'll deal with along the way, but some of that, most of that not in this half. Okay, so first of all, notice at the very bottom of this page, I kind of snuck in an important point. You know, anywhere in my presentations where I have a couple of red asterisks sitting there, that indicates something is important. Something that can be put into a test question. So it says here, a foundation supports the building structurally, and it keeps moisture out and organisms away. So that's a big part of it. So this is a pretty beat up, ugly pier foundation, seen better days, but you can still kind of see the whole idea is to not have the moisture come through from the concrete into the wood. So we typically have some kind of metal flashing, some kind of protective membrane or something to keep moisture from migrating from the concrete foundation that won't decay up into the wood that will decay when you're dealing with residential construction. Okay, so let's move along to the next page here. Okay, another title page. It's the same message down at the bottom, but first of all, dealing with foundation requirements. So what are foundations for? Well, over on the left you see foundation support the structure. Vertically, there's vertical forces to worry about, and there's horizontal forces. So the vertical forces support the dead loads, and the vertical live loads, the building, weight of the building and such. So what's a dead load? What's a live load? Well, a dead load would be something that's dead. Okay? Well, no, you've heard about, when we talk about the dead weight. The actual weight of the building, the weight of the structure. In this case, we got a sign here. The weight of that structural steel is all that support. It weighs something and it's putting weight down on the ground, onto that footing. So that's something the foundation does, that footing. Now this footing, by the way, has got a concrete cap on top of some piles that have been driven into the ground in this case. So they all are part of the foundation. So dead loads are the original material, anything that's attached to the building or the structure. That's a dead load. A live load would be, well, us, if we're up on top of that sign on that platform up there, well, we're a live load, we're alive. But it also includes, well, it can be birds flying up there, they're alive. But it doesn't have to be actually alive. It can be inanimate objects that are just temporary. So a live load can be, well, a bunch of snow up there on top of that thing. That adds weight. Or wind that's blowing on that thing. So live loads are temporary loads that are exerted on the structure. In your building, in your house, you have furniture, and that's considered a live load, even though it seems kind of unanimated. Has nothing to do with animation. So then when you look at the horizontal forces, well, what horizontal forces? Well, for one thing, if you had a great big old sign up there, the wind blowing sideways against that sign could blow the thing over if you don't build the footing and the structure strong enough. It's a tremendous force when you have that great big surface up there that's, if it's solid and you have wind blowing directly on it, it can be causing a lot of twisting action down at the footing. So it can create moment forces, twisting, or torque forces. Moment and torque are the same thing. So you resist the horizontal live loads, like the wind loads. And there could be other, well, in this case, this sign is off-center. It's not nice and balanced, and so it's leaning out for some reason. You want to get that sign out as close to the people on the highway as possible, and you can hang it out over your property in the air. Well, that's a type of moment force, but it's still considered a horizontal force in that respect. It's causing more than just simple vertical pressure on the soil. There's twisting action. Okay, so that's a lot of stuff to look at in one picture. But anyways, so there's three basic ways that we can support the forces, that we support the weight of the building on a foundation. The foundations support the forces in three ways. By flotation, and so you see that outrigger sinking into the soil. Well, that's not good. That outrigger might be part of a crane or some other heavy equipment, and it's sinking into the soil. Well, we need a better platform. The soil's too soft for that, so we end up putting a pad down. And so typically every crane has various sizes of pads that are usually made of timber, of lumber, built together in some fashion. There's some fancier ones that are made of some other materials, some synthetic materials, but they distribute the load out over a larger area, so it's not punching a hole into the soil like this is doing. So it's just like snowshoes. You see the snowshoes here? They spread your weight over a bigger area so that you can stand on top of the snow. You step out of those snowshoes and you might be like the guy on the top of this picture where its only thing sticking out is the hands. Well, no, I staged that. I put those gloves there to pretend as if somebody sunk into the snow. Not real. Okay, so that's flotation. So our houses, many of our concrete slab on grade houses, they're sitting on the ground, and we call that a floating slab. It's considered floating, even though the concrete weighs more than the soil probably. It certainly weighs more than water, so it's not really floating like a raft, but you can think of it like a raft, and that's the way we speak of those kinds of slab. Any kind of a slab on top of the ground is floating on the ground at some level. And depending on how good the structural quality of the ground is, it could slowly be sinking over time into the ground. And that's what happens here in Louisiana. Okay, so flotation, that's the first way. The second way is direct transference, something that just doesn't happen around here in Louisiana. But if you get a place that has outcropping of rock coming up out of the ground, like in this left-hand picture, you can build directly on that bedrock. That's solid stuff. No better footing, especially if that structure of that rock is pretty stable, not cracking and falling apart. Look at these piles up top. They're piles that are driven into the ground, but not just into the mud. They're driven down until they hit bedrock, and then they'll cut them off at the appropriate length. In this case, they bundle them together, and in fact, those piles, those 4 bundles of piles were used as part of a pier system back in the day when that stern wheeler that's now a museum in the background, it used to be using them to tie up to and bump up against and stuff. And then you've got ski lifts down here in the bottom right-hand corner, which could be mounted and directly to rock. And a lot of ski lift towers for downhill skiing are mounted directly to rock, because it's hard to go and mount and build a foundation system up there on that hillside like that. If you can find some good rock, really, you can do an elaborate connection with epoxy grout and things like that to connect that thing and mount it. Okay, so that's direct transference, the second way, something that doesn't really work in Louisiana. What's the third way? It's friction. So this picture on the left next to the words is a pile driver, and it's used to drive a pile. And in fact, the picture that we're looking at is actually a precast concrete pile. It's a concrete column or post that's being driven into the ground. Well, that's not going to rot, so it's very durable, but we drive wooden piles in all the time. And so why is it that a wooden pile doesn't rot? Well, it only has trouble or any danger of rotting up close to the top surface of the ground where the organisms are. You get down deeper to the bottom, in the lower end of that wooden pile that's driven in the ground, anything below about 10 feet, you're not going to have any bugs down there. That's all going to be clean. They need oxygen, they need moisture. Well, the main thing is oxygen. They also drive steel piles into the ground, and you say, well, they could rust. Yeah, but only in the top part. So, because in order to have rust, you have to have oxygen. So, anyways, so when you drive a 2x4 in the ground, you can drive it till you get a decent amount of friction in the ground, that 2x4 stake is rigid, and that's basically how a pile works. You drive it down till you get enough friction. But it's more than that. The pile that you drive into the ground, even though it's just going into dirt, it's not just the friction, it's the fact that the bottom of that pile is standing on much more solid ground than what you're at the surface, than what you have at the surface. So the material gets denser and denser the deeper you pile it. You drive it into the ground. So we drive these piles to refusal is normally the terminology we use. I had to click on something, so I got to click on something else here. Okay, so this picture kind of shows it's not the way it really works in the real world, but what's true is that the lower density, less compacted materials are close to the ground, but over time the weight of everything on top of the other materials makes it more compact, more dense material the deeper you go. And so the piles are being driven down to higher density material that supports the load of the building. And so that's the trick about the whole thing. If you build a slab on grade house and if you had a really good benchmark, you could measure the elevation of that slab of that brand new house and come back a decade or so later and measure the slab height, and the whole thing would have sunk some distance down. Maybe an inch, something. Could be more. It just depends on where you're at. And gosh, if you're in an area where they have reclaimed the swampland, such as in Metairie and Kenner is a good example. But even in Baton Rouge, we have plenty of reclaimed swampland that we've built subdivisions on all around especially outside of the city. The original Baton Rouge city was good ground. And then as we've grown out into the newer areas, they've mostly had to reclaim swampland. And you wonder why we have flooding problems out there. Far less problems in the original city. Same thing, you go to New Orleans, the original city of New Orleans, the French Quarter, is really about the only ground that's above sea level. Okay, well, I digress. So piles really help. Let's see. So 3 common foundations, and these are all basically supported by the ground. You may call it floating in some respect. In all cases, most of the time when we talk about a floating structure, we're talking about a slab on grade, like the very top one. And this is the most common foundation used in Louisiana, all over the place, because it can, and it's very practical. It's very inexpensive compared to what we have to do in some other areas. And so why is that? Why do we need to have basements or crawl spaces in some other areas? We just can't get away with a slab on grade everywhere. The reason for that is that the ground, when it freezes and there's water in the ground, water expands. And when water expands, it's going to lift up stuff. And so if you've got frozen ground that freezes underneath your slab on grade, it's going to lift it up. And Mother Nature doesn't tend to lift it up nice and evenly, so you can end up having a damaged or at least jacked up slab. So it turns out if you dig down deep enough, the ground never freezes. You can get down below the frost level and you'll have 50-degree temperatures all year round underground. Even here, you dig down deep enough, you get some cooler temperatures like that. A good reason for building a basement in an area that is very cold is to get the bottom of that foundation below where the ground freezes, so that you can protect against frost heaves. That's not something we have to worry about in Louisiana. And in fact, it took me a little while to really gather and understand that there's no such things as basements in Louisiana. That said, there actually are, and I have found quite a few of them. We have a basement right on Baton Rouge campus, on the Baton Rouge Community College campus. The student center is built on top of a foundation of the old state police headquarters. So there's actually jail cells down in that basement. So it's a miserable place with mosquitoes and the whole bit. Because basements are hard to maintain. The LSU quadrangle of the original quadrangle at LSU has basements. And in fact, there's tunnels going underneath that connect up to those basements and connect up to the clock tower and stuff, because I've been down in them. Now, I had to be in Tyvek suit with respirator and flashlight, and there were some weird critters in there. I met up with a skunk one time. That wasn't fun. When I was having to do drafting and measuring of as-built what the existing pipe for chill water, steam, and hot water for an engineering company years ago. Anyways, I digress. These are different, there are variations on a theme. And by the way, the middle picture is, you could think about pier foundation houses as being kind of like that too, except you've got a whole series of piers. But they are basically sitting on the ground. They're not being driven into the ground the kind of traditional piers that we have here. Now, you can have drilled piers that are more like piles, and we do that here in Louisiana also, where you drill holes in the ground and you fill them with you drop a cage of rebar in there and fill it up with concrete. We'll talk about that in more detail later, how that's done. Here's an example of a pier foundation, a single pier, but normally you have a whole series of them underneath for a pier foundation house. A lot of the old houses were in our region here that are on piers. They just put some masonry block down or a concrete pedestal, and they just sat it on the ground and kind of kicked the topsoil away and sat it there and built the house. And they wonder why we have settlement problems. You're supposed to be able to distribute the weight over a larger area than that, and that's why those piers sink down. You need a big pad underneath there to support a weight, just like the outrigger on that crane needed a big pad to distribute the weight over a larger area. So in this case, it's a 2-foot by 2-foot pad, and that's enough to distribute the weight. So if you had soil that can only support 1,000 pounds per square foot, which sounds like a lot, but it really isn't. 1,000 pounds or 500 pounds per square foot is about what we get in Louisiana, whereas in lots of parts of the countries they get 3,000 or 12,000 pounds, that sort of thing, per square foot of supportable ground. So it's why we have trouble with buildings sinking here, is because of our ground just being all this sediment. There's lots I could speak about here, and I tend to get carried away here, but I just point out that you've got to make that pad that concrete column sits on strong enough so that column doesn't just punch through like a paper cutter through it. So we put reinforcing in there. We put reinforcing to connect the column to the pad. We also put reinforcing a mat of reinforcing down at the bottom. The place that reinforcing concrete rebar is supposed to go is where the concrete is being stretched apart. Where it's going to want to crack is where the concrete is being stretched apart. Concrete is only strong in compression, and when you start putting concrete into tension by stretching it apart anywhere, then you need to put rebar there in order to combat that. The concrete can't take it. Steel is very strong in tensile strength. Concrete is not. So when you combine them together, it's kind of like the chocolate and peanut butter. You get the magical combination here. Okay, so that's just giving a preamble to that concept. We've had lots of foundation failures all the time. I see them all over town, and not just in Baton Rouge and Louisiana. I've seen them up in Canada plenty of times. They happen all over the place. People screw things up because they didn't think things through, or they didn't understand it to begin with. The Leaning Tower of Pisa is a famous example. That step is not so famous, where it's just sinking because you got a very heavy solid piece of concrete for the steps, and it's literally sinking the slab that it's sitting on. And you can see that it used to be up higher at one point. It's pulled away from the sliding under the door and to the left of the door. Here's a foundation failure. It's sloughing off into the water to some degree. And on the left-hand picture, the right-hand picture, you've got brick. Brick tells no lies. It's like a piece of glass, and so any change in shape, it'll let you know with those cracks. So those are failure that just shows up in the brick. It doesn't mean the brick is at fault. It means that there's a problem with the foundation. Here's an example of where the sidewalk was not put down properly. I know that it was poured right on top of the topsoil. They never worried about any of that because no one was looking and nobody would ever notice or care until it was a long since paid contract. This is what happens all the time where contractors will take shortcuts. Get stuff in my way here. Okay, so let's see. So foundations need support. So the first thing we do is we strip off the topsoil for any foundation. And then you want to make sure you're digging to original ground. If you have to bring in fill to build your foundation on, that takes an elaborate amount of work to do it properly, to compact the ground when you bring new fill in. Most projects, they don't do it. They don't do it right. When you see how many a house, they bring in a whole bunch of fill to bring the building up to a higher elevation, but there's the grade beam, the bottom of the perimeter grade beams and the interior grade beams are supposed to be going down to original ground. They have a hard time figuring out what original ground is in many cases, and then you wonder why you've got settlement problems. Okay, maybe you don't wonder, but people do. Okay, so let's see. Where was I? Lost track because I started spinning this wheel. Okay, there's some broken concrete where it pivots up, and so as it's lifted up maybe from something solid a few feet back or a foot but two back, it literally pivots like a teeter-totter and lifts up and creates a tripping hazard. This building fell over, and it wasn't an earthquake, even though it happened in the Philippines, in Manila. They have plenty of violent earthquakes in that region. This was from a basic foundation failure that started to lean and lean and lean. And they had everybody out of the building by that time it collapsed over and started touching the building across the street. But still, you've got to balance your loads. When you got a disproportionate weight on the building, you got to make sure your foundation is built to take care of that extra weight. So I've got two terms here with foundation settlement. There's uniform settlement, which is not so disruptive because the building is sinking evenly, so it's not tearing itself apart. I mean, you might have to deal with the outside and re-landscape to lower the ground around it, and so that you can slope the ground away to send the water away from the building. But that's not anywhere near as disruptive as differential settlement. The bottom picture, where the building is not sinking evenly, which is what happens most of the time in the real world, all the time. That's what we see as structural damage and stuff from over time. And there's plenty of examples of where that's happened. So that's differential settlement. So there's uniform settlement versus differential settlement. We'll mostly focus on differential settlement. There's a couple of different kinds. But in general, for instance, there's compound and transition settlement. Those are just variations. Those are more extreme versions of differential settlement. So this picture here is kind of showing you the transitional settlement. You've got some part of the building on really good ground, and the rest of it's on very poorly compacted fill. So that, but it's just basically an extreme version of differential settlement. So I will stick with the terms of uniform versus differential settlement and not get into the weeds too much on transitional or compound. So here's a good example up top where you want to build a house into a bank, into a hillside. That's something that doesn't happen here because we don't have any hillsides around here, but I mean, not very, very few. If you squint, there's kind of a hillside along Highland Road in some places, and that could happen. But when you go and try to flatten the ground out to bench and terrace this, what often happens, you end up bringing some of the dirt out to make the bench wider. And so maybe a half or some portion of your building ends up being built on fill. And the way you combat that is by having your foundation go down deeper so that it gets down to original ground again, so that this doesn't happen. Otherwise, I've seen buildings where 3 years later the building has to be condemned because it can be that bad. And that doesn't tend to happen as much here, although it could. You know, if you bring in fill to fill a hole and you just dump it all in there and tamp it down and declare victory, you generally have, when you actually bring in fill to compact it for a foundation, you need to only bring in no more than 6 inches at a time, and you compact that, and through quite a process, and bring in another layer. Anyways, so you can have soil that's better quality, maybe at one end of the building, and poorer quality, even when it is there by Mother Nature. So sandy soil can have a good load-bearing capacity. Silty and clay soil, not so much. So we have mostly clay and silt in Louisiana. So it's a fairly poor soil to be trying to build on. Great to grow stuff, poor to build on. Okay, so settlement causes, you can have poor soil conditions, you can have poor building site preparation, meaning poor compaction, poor ground preparation, not enough compaction. All these things can combine. You can have plumbing leaks that are eroding the soil out from underneath the building over time. Or you can have tree roots that are sucking the moisture out of the ground, and that can cause settlement problems. But more often in Louisiana, we have trouble with other kinds of causes where the tree roots actually lift up the buildings. We have aggressive tree growth in Louisiana. Maybe not all the time, but throughout the time and over time, you have tree roots that destroy foundations by uplift. And then you also have clay that it causes trouble with uplift, because all clay is expansive. And so when clay gets wet, it expands and it can lift up the building or lift up the slab of the driveway. And when it dries, when you loses the water, then it shrinks. And the problem is it doesn't even come back to the same places. So then you end up with pockets of cavities underneath your foundation or underneath your driveway. And so it's more of a problem on driveways, is where it shows up. When over time, you end up with hollow cavities, and then a truck drives over and breaks up that concrete. The idea and the theory of roads is to have your pavement completely, continuously supported by the ground underneath. And when the ground starts to do tricks like that and leave cavities behind, not only does it give a good place for the ants and the other critters to roam, it gives you a place for the concrete to break into. And then that's how roads and driveways fail. Okay, so let's see here. Now, in cold climates, you have this frost heave issue that we just never have in Louisiana. The frost heave, the foundational area we have to worry about for a 100-year freeze in Louisiana is 4 inches. So every foundation is going to be below 4 inches. That's just never a problem. So frost heaves, a non-issue here in Louisiana, particularly in southern Louisiana. I mean, we've gotten frozen temperatures, but never frozen ground. It just doesn't happen. Get a little ice puddle maybe that freezes over, and that's about all you can, or a little water puddle that freezes over, and that's about it. But this building here, you see the yellow line on this picture. I know it's kind of a grainy picture, but it's a good one nonetheless, until I can find something better. That is where the yellow line is showing you that the ground isn't going to freeze on the first left-hand side of the picture, because the bottom of the foundation is below where the ground freezes, so you're just not going to get any uplift. But on the right-hand side of this building, the ground freezes lower because the ground is tapering down. You don't have the protection of more ground to insulate and keep it from freezing there. So it's dipping down, and so it can cause the building to get damaged at that end and cause foundation problems. So the way we combat that is we let that end of the building have the bottom of the foundation step down deeper. So you do that right from the beginning, knowing that you want it to be exposed. Maybe you can have a driveway or a doorway or something, and you want the ground, that basement to be at ground level at that end. Okay, this picture here is some frost heaves out in the wild. They kind of look like alien suction cups have landed on here, and or crop, I don't know, gravel circles. I don't know, not crop circles. With road building, we don't have the ability to go and build the foundation of the road down below where the ground freezes. Not an issue here in Louisiana, but in places where they get very cold weather, the ground will freeze underneath that road. However, there's a trick to this that we can use, and what they do in road building is they don't let the ground that can freeze have any water in it. They make it sure it's a free draining gravel that they put under there, so that the water and give the water a path to run to, so that the ground that's going to freeze has no water in it. So then it doesn't matter if it gets cold. It doesn't matter if it shivers. Well, no, it won't shiver. So, but look at this example on the left. This patio that's all broken up because of frost. Something that just wouldn't happen in Louisiana. On the upper picture, there's so many, there's plenty of roads that were not done properly, and they have all these kinds of problems. And when you get on one of these roads, it's quite the experience. The coins in your ashtray spend half their time in midair in that road, and your coffee is in midair half the time too. Pretty bumpy. And this is the kind of thing, and it's not always that extreme. You can have places where the road failed and end up getting frost heaves, and next thing you know, it has to be repaired. So they do have flaws in highways. Plenty of highways have been built over many years, and where they didn't have the kind of equipment we have. When you're building a brand new road nowadays, they're less likely to have any of those issues. There's some old abandoned buildings in a mining town that was just sitting on the ground, and they've gone and lifted up. And so there must be something a little different in the ground, maybe at the two outside ends of this picture, that are causing more uplift than you're getting in the center. In some parts of the country much further north, I'm talking about Alaska, the Northwest Territories, the Yukon, they end up with some ground that's frozen all year round. It never is not freezing. And so they call that the permafrost, and there's actually kind of a funny little geological kind of culture that can be in the ground from that they want to preserve. But when you're building a building in that environment, one way to do it is to auger holes through that ground. You drill through and you install some piers, so you end up with a building on stilts. So that's one way to do it. Or you build a structure out of geofoam. It's like a styrofoam foam material, but it's called structural foam, that is strong enough, that is denser and insulating, and stronger than the soil in Louisiana, so it can easily take more than 1,000 pounds per square foot of load, and you even pour your concrete on top of it. And you can actually have a concrete slab that's sitting on top of foam, so that it's well insulated from the temperatures. And if the ground is always frozen, they don't have to worry about settlement problems either. Okay, ice rinks have the distinction of being able to, even in Louisiana, create a frost heave in the ground, because you got this refrigeration system right there at the ground, and so it can tend over time to freeze the ground and cause a frost heave that damages the ice rink. So we often have to have warming tubes that are keeping the ground underneath the rink warm enough to keep it from freezing. That might just be having a whole bunch of tubes in the ground that you're pumping water through. It doesn't have to be hot water. It can be cold water, because it's still way warmer than freezing. So that's one thing. And so sometimes they just have a water glycol solution, kind of like your radiator in your car, and they're pumping this stuff through to have a cycle. And then they'll put some styrofoam on top of that, and then put your concrete slab. So the river center is built like that downtown, so that they can have that ice rink ready for our hockey players and for us to skate at Christmas time and stuff like that, to prevent that. But so this can crop up sometimes within buildings where they build the refrigeration unit, the freezer units, whatever, into the building, and then you got to make sure that that concrete slab is set up and prepared for that. So that you can deal with the combating frost heaves even here in Louisiana when you're dealing with refrigeration of some sort. There's a term called liquefaction that I want you to know. It's a fun little word, hey? Okay, so the idea is in an earthquake, ground made of clay and silt, especially if there's moisture involved, while it's being shaken by the earthquake, can act like a liquid and literally sink buildings into the ground, nice and oftentimes not evenly. And so you can end up with things. So we call that liquefaction. It's where the soil acts like a liquid during the shaking. So that can happen in earthquakes. It can happen on your job site when you've got a train nearby shaking the ground, or a pile driver, or some big heavy compacting equipment. So you have to be very careful around excavations and such, that you're not causing, some hazard at least. Okay, so with earth materials, let's start looking at the materials themselves that we use from the earth as part of foundations. So a boulder is too big to fit in one hand. It's a two-hander, whereas a cobble can be lifted with one hand. Of course, if you're Shaquille O'Neal, I guess you can lift a boulder with one hand too. But coarse-grained soils are the ones that we build with most of the time. I mean, there are times where we'll use boulders and cobbles. I mean, around bridge abutments to keep the river or the creek from eroding the foundation, we'll use big, what we call riprap, and that's made up of boulders. A lot of times, of course, in Louisiana, we don't have boulders, and so a lot of times we'll end up using chunks of concrete for the riprap and stuff. But anyways, back to coarse-grained soils. That's gravel and sand. Now, gravel can also be called a fancier name. It can be called coarse aggregate. And then the sand can be called fine aggregates. So the aggregates are the coarse-grained soils. But anyways, gravel, individual particles can be lifted between the thumb and the forefinger, so you can pick them up individually with your fingers. Sand particles, generally too small to be lifted individually. You're going to pick up a few grains at least, So that's a simpler kind of a way to understand these particles in some kind of a real-world kind of a way. But the definition that I need you to know between gravel and sand, the size where we stop calling it gravel when it's called sand, is anything that's slightly smaller than, anything less than 4.75 millimeters, or about 3/16 of an inch. Now, you might remember 3/16 of an inch fairly well, but 4.75 millimeters is the industry standard in every textbook and every gravel pit. That's what they use. So you need to know that number for a test question. So just watch that number. You either know the number or you don't on that test question. So 4.75 millimeters. I'll mention it a couple of times here. A couple of times more, I guess. Now, then there's the fine-grained soils, such as, the silt and the clay. Individual particles are too small to even see with a naked eye. Not really. I guess if you got really good, fresh, young eyes, maybe you might be able to see some silt particles. That's pushing the envelope a little bit. But so under the microscope, silt particles are roughly spherical. Roughly they're ball-shaped or round, kind of like what most gravel and sand particles are to some degree. They're not perfect round. None of them are perfectly round, or they most of the time anyways. But clay particles are nothing like the shape of any of these other particles at all. They're all plate-shaped is what textbooks call it. But when you actually see it under the microscope, and I'll show you a picture in a moment, the clay particles are more like cabbage leaves or something. They're not just flat metal plates. I mean, they're not metal, but they're not mineral plates or they're like stackable dinner plates or anything like that. They are more like leaves, piles of leaves together. Okay, so let's go start to look. Now, when we talk about solid rock, the definition of solid rock would be a continuous mass of solid mineral material. Generally the strongest and most stable of earth materials. If you can build on top of rock, solid rock, you've really got a foundation already. I've built buildings and structures, including bridges, on top of solid rock where you really didn't need a footing. We were just trying to connect to the rock, and the rock became the foundation. And an incredible foundation it was, hey? And then soil is generally considered particulate matter, everything from the gravel and the sand to the silt and the clay, are various particle sizes and shapes, and different sensitivities to moisture content. So the worst of all to build on would be organic soils. When you look at topsoil, every construction project pretty much, they will strip the soil off before they build the building, and they pile it up because they can use it later, sometimes or most of the time really, for the landscaping at the end. So they'll shove it over in some corner out of the way to be used later, or at least some of it to be used later in many cases. But you don't build on that, or you shouldn't. Now, most of the sidewalks around BRCC were poured right on top of the grass. So they didn't care, and nobody was watching or paying any attention because it didn't really fall under anybody's inspection regime. And that's what happens. So very often, crappy work gets done when it's not being overseen. Okay, so the soil properties. Now look at this picture here. It looks like a bunch of gravel, eh? Chunks of gravel or rock of some kind. We're actually looking at zoomed in picture of sand particles. Now these are well sorted, meaning that all the particles are about the same size. So that's not normally how most sand samples that you're going to look at under a microscope, you'll have large, medium, and small, and very small particles. And that's not what you're getting here. But these are sand particles magnified. So a well sorted sand, water would flow through more easily because you've got all these holes in it that the water can pass through. And that's how also when you're talking about gravel that's well sorted, it makes great drain rock where water can flow through it. So behind a retaining wall or under a slab before you pour concrete, the ideal stuff would be a well sorted gravel and or sand mixture so that the water can flow through it, so that you won't have a whole bunch of water sitting up against the bottom of your concrete slab. That's the best defense against having a wet slab. Now what most people do is just put Visqueen, which is a brand name of a plastic polyethylene sheeting. They put that down, and that's what they declare victory with that, and then wonder why they still have wet slabs. If you don't put a free draining material underneath first, then any flaw in that plastic and the water will find its way through, and you'll still have moisture coming up through your slab. Okay, so I digress. Get off topic. Not hard to do. When you have a bunch of round materials, though, it's like a Chuck E. Cheese ball pit where when something steps in it, it can push and you don't interlock. They kind of depart, just the way you jump into a ball pit at Burger King or wherever your ball pit is, and you sink in there, disappear into it. So the best aggregates in general, as far as structurally sound materials to build on top of for anything, would be angular, crushed rock, crushed sand particles, everything crushed. So desert sand is the worst sand to build on because it is very round. It's been blown around and weathered and ground, so it's very round under the microscope, very round little balls. And it makes a terrible concrete. It makes terrible structure to build on because of that. Because the sand can just erode out like an hourglass out of the from underneath the building. But it's true about the shape of large rocks, small rocks, large sand particles, small. The more angular, the more interlocking you get. Okay, so that's another aside thing that's not on this page yet. I'm talking ahead of myself a little bit. So, but look, these are sand particles. Now let's go look at the next size down. That's the silt particles. So for the fine-grained soils, remember, that's the silt and the clay. Not ideal to build on, but sometimes, like in Louisiana, it's all we've got. All we've got around here is mostly silt and clay to build on. It's what we have. So the silt particles are still basically like the sand particles back here, except they're much smaller and they don't have a lot of color. As you zoom in, you're kind of getting a grayscale look here, but you don't see the same color variation generally. But that, who cares about the color with silt? Hey, no one sees it. You got to have a magnifier, a microscope really to look at it. Now, when we're talking about particle size, if we had a perfect cube of stone, and we had it like a 12-inch by 12-inch by 12-inch cube. We have a 1 cubic foot cube, and it's all perfectly cut nice. So if you measure the surface area of that cube, you've got 1 square foot on each side. So there's 6 sides to a cube, 1, 2, 3, 4 around the sides, and then the bottom and the top, that's 6 sides, 6 square feet. So if I go and split that in half, now we've got 8 square feet. And it's the same material, but we now have 8 square feet of material. So it turns out that as as you break it into smaller and smaller pieces, the same material, and keep it all collected together, you keep having more and more exposed surfaces, more surface area in the material. So the smaller the particle sizes, like clay, silt and clay, as you get down to those sizes, you have more surface area for the water to cling to. And so then, as you get down to these very fine particles, you have so much surface area for the water to cling to, you can hold more water in the material. So you can hold a lot of water in silt. But it also makes it slippery, all these surfaces, when you have so many of them. So that's why you can walk out in wet silt and wet clay, and it's just gushy. So it's a horrible thing when you're trying to put a building on the material. When it gets wet, it's gushy. That's not great at all. So when wet, it may be subject to what we call liquefaction, where when it's being shaken, like an earthquake, well, earthquakes don't happen very violently in Louisiana, hardly at all. We can barely measure them with instruments. We can't hardly ever feel them. But you can have a train going by, or you can have a pile driver nearby, and so that can cause the soil to act like a liquid. You can have trenches collapse because of it. You can have big compactors compacting soil and vibrating the soil, and things can sink into the soil because of that. So liquefaction is the act of the soil shaking. So I was talking about that a little earlier. But but you have trouble with drainage because the soil can hold so much. It'll hold it for quite a while. So when we have rain down here in the south here, we often find that the job is just a mucky job site for days and maybe weeks before it dries up. Whereas up where I lived in Western Canada in British Columbia, it was a semi-desert region, the valley that I lived in. You pour some water in the ground, it disappears, never to be seen again, pretty much all the time. The ground is dry, it's sandy and rocky, and it just disappears. Water, free draining material. Okay, so let me move to the next size. Remember, this is silt. So now look at the other fine-grained soil. It's even smaller than the silt. It's clay particles. And oh my goodness, look at this stuff. Clay particles. That's not round. It's not even nugget form at all. Clay particles, they call it plate shape, but I would say it's leafed shape. The textbooks call it plate shaped. Yeah, that sounds like a very laboratory name. I say it's more like a pile of leaves all squished together. This is how the stuff breaks down. A lot of the clay particles started off as granite, and over time it turns into this leafy material, flakes of the crystalline structure that's broken down over time into this. So clay particles, when they're wet, it's a gooey mess, the worst of the worst. And it expands, too, into a larger volume because it has all this surface area where the water clings to the surface of all these leaves, and so it expands in volume. And then when it dries, it shrinks in volume. And there's electrostatic forces that bond all these leaves together, so it can be rock hard. So clay can go from being rock hard when it's bone dry to being this goose poop mixture of mess that's the worst of things to walk around in, the worst to build on of anything. And that's what we have in Louisiana, is mostly clay and silt and clay, with little pockets of gravel in places where in the elbows of the river, or where the river used to be. So we get most of our gravel and sand from the elbows of the river. They dredge the river to get it, to make for road building, for anything we use gravel for and sand for. And or you can go into places where the river used to be, and you can predict and find the elbows of rivers gone by, you can find pockets of sand and gravel there too. So there are some gravel pits in what we would call land sources. Although when you dig a hole in Louisiana to go after that gravel, it'll be a wet source and very quickly, because you dig a hole in Louisiana, it fills up with water pretty quick. Except when we have a really dry period, you might be able to get away with less of that. Okay, so that's what clay is. Now, two terms you need to know about, and I've kind of mentioned it a little bit along the way here, but there's well-graded soils or well-graded gravel and sand compared to well-sorted soils or well-sorted gravel and sand particles. So here we are. The well-graded means you got a real good balance and mixture of large, medium, and small, and very, very, very small and very, very small particles. And it makes it a very dense material, and there's a lot of surface areas because you're combining all these together. And so this is the secret to making a really strong concrete mix or an asphalt mix or a roadbed aggregate mix that's going to go underneath as a foundation for your road. This works really, really well. Now, that picture on the left, that's what we're looking at. Now, the two pictures are not quite fair because the well-sorted picture over on the right shows angular rock. And the angular rock, actually, there's something you get from having crushed or angular pieces. When you compact them together, you kind of create a puzzle that interlocks. And so you get better connection from that. So you might notice that a train track tends to put rock down like this because it helps to be more stable. You can have that with the well-graded mixture too. So those are two different animals here, talking about angular material compared to round material. The very strongest mix for concrete and for aggregates and everything else, every other mixture you need it for, would be well-graded and angular. But if all things were equal about roundness or angularness, if those are words, would be, if you have a bunch of particles that are the same size compared to the denser, well-graded mixture, the well-graded mixture will win as far as structural strength. But if you need water to pass through it, having it well sorted really helps because you're giving a cavity for that water to flow through for drainage. So behind a retaining wall, you don't want water trapped behind your concrete retaining wall. You want drain rock, and the definition of drain rock basically is a bunch of well-sorted, all the same size particles. And if you want sand for the playground, they don't want all that dust because they want the kids going home cleaner. They'll use well-sorted sand, and so it kind of all the same size particles. Whereas sand used to make mortar from masonry, for the mortar material that you lay bricks and blocks into, will be well graded from large, medium, and small, from coarse sand down to very fine sand. Then you mix that with masonry cement, which is Portland cement with a hydrated lime in it. Concrete, the best, strongest concrete, will have the largest aggregate size you can stand to have in your mix, depending on how close the rebar is to each other, how big the rebar is, the spaces between, and the size of the thickness of the slab, the thickness of the wall, that sort of thing. You'll have certain limitations, but the largest aggregate size that you can stand to use, well graded all the way down to the small, fine sand particles. And then that makes the strongest concrete, requires the least amount of the most expensive ingredient in the mix, the Portland cement, which glues all those particles together in a chemical reaction with water. So again, I keep digressing or moving away from the topic here, but I've just so much I want to tell you. I can't tell you it all in one day, so let me move on from here. But remember, well graded, you've got graduation or gradation of sizes. Whereas well sorted, somehow, and usually through a gravel pit, they'll use different screen sizes in order to sort them out into different, so you get a bunch of particles that are all the same size, whether they're big chunky things like this or sand particles that are all the same size for a playground. Most free draining. Yeah. Okay, this page I've thought about getting rid of at times. What I want you to understand is the load-bearing capacity. That's the second column on this page. Yeah, so the bedrock, you can have easily 12,000 pounds per square foot. So a square foot, 12 inches by 12 inches on the ground, a 1 foot square, 12 inches each way. You can put 12,000 pounds on it. That's like the size of a couple of pickup trucks on 1 square foot. And I've seen ground, and I've dealt with, and I've built on ground up in Canada that could hold way more than that. So that's a kind of a minimum for bedrock. Whereas you get down to the bottom of this page, where the kind of soil we have in Louisiana is the clay and sandy, silty, clay, silt combinations. And you're looking at maybe 1,500 pounds, maybe 1,000, maybe 500 pounds per square foot when the clay is wet. And so we have to build for those kinds of circumstances here in Louisiana. It's why we have trouble with sinking foundations all the time, and you got to make your slab on grade really strong if you want it to hold up against that. So that's the problem. We have plenty of pluses around here. We don't have to worry about mudslides. The ground is relatively flat and it's weathered material. You don't have to worry about radon gas. There's all kinds of things we don't have to worry about in Louisiana. So yeah, every region of the country has its pros and cons. And that's half the fun of it. But you need to understand how to build in all these areas, even if you don't plan to leave Louisiana ever. And I know from marrying somebody from Louisiana, it's hard to leave Louisiana. I don't know if I could anymore. I've gotten used to the food. I've been here long enough. But feast or famine, that's the nature of construction sometimes. And some of these companies that you might like to work for because you command high salaries, sometimes they need you to go work somewhere else for a while. And so you need to understand the issues before you get there, so you're not starting from scratch. You need to understand the variances within these different regions of the country. They help you to communicate with other people too. Okay. So that said, let's look at the aggregates. I'm going to skip through this fairly quickly along the way, but yes, there's different aggregate samples we can look at, and mostly I'm introducing something I've just already said, but here it is in writing at the top here. It says coarse aggregate and fine aggregate, and basically that's sand and gravel by most people's definition. So that's what I will use. So the coarse aggregate is the gravel. Again, that portion of the aggregate that is retained on a number 4 sieve size, which is a screen, or 4.75 millimeters. So I'm not going to make you memorize anything except, again, that 4.75 millimeters. That's what that pair of asterisks, red asterisks, are for. And so anything that's retained on the screen doesn't fall through the screen. Well, that's coarse aggregate. That's gravel. Whereas what falls through, what passes through the fine aggregate screen, that's called sand. Now, there is another sieve size, a number 200 sieve, which has a grid of about 3/1000ths of an inch, or 74 microns, a very small particle size. Whatever falls through that screen is called silt. So that's the definition of if it's too small to be sand, it's called silt. So then the weird one is the clay, because that stuff is much smaller and it's not even it's not round enough to fall through a screen. You know, it's different. Okay, so let's pass up there. There's some definitions that I won't go into here, but there are some things. Bank gravel comes from the bank. You're not going to have that in Louisiana so easily. It's going to come from the elbow of the river here. There's crushed gravel, where you've got surfaces that had to be artificially crunched up until at least one face is fractured. There's crushed stone, where generally all the surfaces are angular. Crushed rock, blast furnace slag. There's some things in here, but I guess the only one that probably comes into play for us is crushed gravel. You at least have one surface that's angular, because that's about all we can get in Louisiana sometimes. But it's all artificially crushed with a crusher that takes rock and breaks it down into smaller rock or into gravel or sand particles. There's this unified soil classification system. We do have a little lab exercise, but everything is well explained there, and I'll get to that later. But here they're kind of describing these codes, GW, GP, GM. you'll be able to understand from the lab what we're talking about. I'm just introducing the concept here. Yes, there's well-graded gravel, so WG for well-graded, or graded well, graded poorly, GP, and on down the line. We'll come back to that later, but just, it's more to come, and more pages of that same thing. Okay, the effects of moisture on clay. Remember, because it has so much surface area with those leafy surfaces. Oh my goodness. So when clay is dry, it could stand up like a bank. I've got, up where I lived in, close to the American border in Canada, there's in that Okanagan Valley in British Columbia, there is clay banks that go up 1,000 feet, and they've been there forever. And every now and then some turkey builds a house at the top, or a bunch of houses at the top of that, and then they start watering the grass too much or have a leaky swimming pool, and next thing you know, the whole clay valley, the whole clay bank with the subdivision slides down the hill, and because nobody paid attention to that issue, what they expect. But in nature it happens too, where you can have over on the right-hand side of the page where you've got this clay bank that literally collapses catastrophically and maybe brings part of the house or all the house down, or comes down and buries something below with the mudslide. And so that's what I was going to show you here, is how you can have these catastrophic landslides that kill people. They can bury people alive. So that's what happened in this little town roughly south of the border, a little closer to Seattle in Washington State, called Osso. That was pretty much the whole town was buried. So at the top you see the existing town, and they're showing you the buildings in red. Down at the bottom right corner you're seeing the town afterwards, and it's basically almost completely gone, because on the other side of that little river they had a mudslide that came down and just ran over top of the buildings on a Saturday morning when most kids were home. So it was just so sad and destructive. So yeah, that when you're looking at, basically, here's probably the best picture. It'd be just blown up a little bit, but you kind of get the idea of what it did. So they had been monitoring that slide, but nobody ever believed it would be as catastrophic as it was. And in the end, trying to save people, the people in that building probably were saved because they were at the edge. But that house was basically pushed off its foundation and pushed for hundreds of feet, Anyways, had a slide on the other side of the border back in the 60s where a rock face from an earthquake collapsed and sheared off and then hit a lake down next to the little town of Hope and washed the lake water up the other side of the mountain, which caused another mudslide to come down. And so the combination of all that just buried the whole place completely. And so a bunch of people were buried alive there too. So this kind of stuff happens around the world at times. In Louisiana, we don't have that issue. We don't have any hillsides to slide. Everything is pretty flat. And so, yes, we have floods, but every area has their other issues. In the South in general here, we do have a phenomenon of sinkholes. So I can remember shedding a tear for, I mentioned this in class, Corvette Museum in Florida that was where there was quite a few classic Corvettes that were lost in the sinkhole. They saved some of them. But that happens because you can have soluble rock, like salt, that erodes away over time, and next thing you know, you've got this underground dome that collapses, and all of a sudden what seemed like solid ground isn't anymore. Right here in the Louisiana area, roughly southish, southwest of Baton Rouge, I think so, if I think about it a little bit, Bayou Corn. First noticed in 2012, in May of 2012, that thing expanded out as it was collapsing, and it started to affect or put some houses in danger. So a bunch of people had to evacuate because it was a salt mine under there that they eventually used to store oil, which eventually when they gave up on that, it was just an empty salt dome, the oily salt dome with still some hydrocarbons in there, and so literally a toxic brew. Anyways, so this kind of stuff happens. There's a lake south of Lafayette called Lake Penier. I don't know exactly how. Penier, maybe. I'm not sure how. Penier. I don't really know how it's pronounced. I keep meaning to ask somebody that might be from that area. But back in 1980, so it was a while ago. But the lake that was only, I don't know, typical Louisiana lake is only a few feet deep. 10 feet deep, maybe, that kind of thing. And this lake went to be from there one day when Shell Oil punched a hole in the bottom of the lake accidentally. Well, they didn't realize that it was an active salt mine, and they punched a hole right into the salt mine where people were working, and so people all survived in the salt mine, scrambling for their lives to get out of that salt mine underneath this lake as the whole lake drained into the salt mine. The creek or little river, whatever you want to call it, that was going to the Gulf from here, from this lake, was running backwards that day. Sucked a bunch of the barges into the mine, which eventually popped up because it had enough buoyancy to eventually pop back up, or at least some of them did. It now is considered the deepest lake. Went from a 10-foot lake to a 200-foot deep lake. So that was quite I've got an interesting video on there. Maybe I should post that in class so that you can view it if you want sometime when just for the fun of it. Anyways, so aggregates we find them wherever we can across the nation. So in Louisiana, we dredge the river. In other places, they dig into the rock, into a mountain. Other places, they might have to dredge rivers and creeks too, but plenty of places they can find the rocks that they need, the gravel. There's different qualities, what we get is just the random stuff that rolls down the bottom of the river and collects in the elbow. So we get more random gravel. But up where I lived, there were certain gravel sources where they were more chemically inert and more perfect to make a much stronger concrete. And some other kinds of gravel sources could be somewhat chemically reactive, have some sulfates in them, and maybe not be a great source for concrete. And so before we understood that, a couple of our hydroelectric dams that were built, we have nothing but trouble with. And others, like the Hoover Dam, were great sources of gravel, no trouble whatsoever. So again, it matters. In Louisiana, we're mostly dealing with weathered materials, so we don't have chemically reactive soils, or with sulfates, we don't have a lot of reactive gravel. It tends to be weathered gravel and sand. So we don't generally have that trouble here. The typical gravel plant of some sort, gravel and sand plant, they'll go and sort the stuff with conveyor belts and screens, and if they need more smaller stuff, they'll take any larger stuff and crush it down to smaller stuff. This is a portable gravel pit where the gravel plant can be picked up on a truck and taken somewhere else. So a lot of times when they're building highways, whenever they can, they'll get the sources right near, because you save on cost when you don't have to truck it too far. So here's an example, just kind of showing you some of these screen sizes. And here's some sample gravel mixes of various kinds. So here's a number 1 gravel, maybe going from 1 inch, largest size, down to maybe a ½ inch. So basically, when they talk about a 1 inch minus mix, that means they're going from the largest sizes, 1 inch, all the way down to some much smaller particles, smaller than what you see here. Here's a round one, number A. So there's all kinds of versions of this. Look at this. AASHTO is the Association of Highway Transportation Officials. That's their abbreviation, and they have a numbering system for some gravel, and they have some testing numbers. There's a bunch of things that there are to know on the industry. I won't have you memorize too much on that, but I think maybe one of the most important mixes for highway construction, and for when you've got a plant somewhere or a facility where you don't need to pave it, but you need really good stable soil, you might use a limestone mix. And so a minus 1 inch limestone mix means the largest aggregate size is 1 inch, and then it goes and graduates down, and all the particles are crushed and well graded from 1 inch down to fine sand, and then they mix hydrated lime in there. So they call it a limestone mix. There's no limestone in there. There's lime powder in there, the same kind of powder you would put on a football field or a soccer field to make lines back in the day, before AstroTurf and stuff. But anyway, so it makes for a really good base under a roadway. So it's usually the last thing they put down on top before they start paving is limestone, a crushed, engineered limestone mix of some sort. And again, there's no limestone. it's lime and the stone mixed together, but it's it's what they call it. Concrete sand will be well graded from large, medium, and small, and asphalt sand, and then there's a mason sand. They are all a little bit different in what they will be, but they're a similar concept of what they grade through. There's a mason sand. Okay, so that said, I'm not making you memorize all that, but just want you to know that there's different products available at the gravel pit. And so you can't just ask for sand. Their next question is, what kind of sand? You want beach sand? That's different from playground sand, and it's different from what you need for concrete mix or a masonry mix and that sort of thing. Okay, let me skip along here a little bit past the geology. Although it's fun stuff, I have to stop. But it does give me an excuse to show you when glacier valleys are cut in the mountains. You get these U-shapes cut in the rock faces from the glaciers. And these lines where they got a chunk of rock that's kind of stuck on the side of the glacier, and it scratches a line along there. So that's where those lines come from. The traveling of the glacier as it's sliding down and cutting away. And then it leaves these characteristic lakes up here because it'll sit there and melt for a while, and then it moves along, and so it tends to create these lakes. The glacier does that, It makes these mountaintop lakes. And this gets me a chance to show you where I grew up in Canada here, this U-shaped valley that's in here. And I kind of lived on that bay that's way over on I don't know if I can show it to you with my cursor here. But anyways, just where I lived in some of the areas. It's all cut by glaciers. We have in the same valley, there's a 100-mile long lake. It's a couple of miles wide in most places and about 1,000 feet deep in most places. And they have a floating concrete bridge. So what you're actually looking at here is the one in the foreground, the closer to us, is the old bridge that was there since the 50s. And then they replaced that since then with the bridge you see on the other side, which has more lanes. It's about 5 or 6 lanes across, whereas the other one was about 4 lanes across. And they basically replaced one with the other one. Skipping along here, probably more interesting in Louisiana is all these soils eventually end up in creeks, which gets transported to rivers, and so we end up with a bunch of sediment in these rivers. And by the time, they might start off in some of these mountain creeks. Some of these creeks can run 35, 40 miles an hour. You can't outrun them. Whereas by the time you get to Louisiana, they might be running maybe 5 miles an hour or 3 miles an hour. And they're carrying a whole bunch of sediment, and they're just slowly winding around. And you see how they create these elbows, and they exaggerate out. And eventually, you see how you can have these oxbow lakes behind it, or false rivers, we call them, where the river used to be, and it kind of cut across. So here I'm kind of showing you the life cycle of that. You get these more exaggerated bends of it. Typically every year you get the spring runoff that's much, much faster, and it can be so much that it can literally cut across there eventually. So it's usually the springtime where it'll shorten the journey eventually of the lake and leave a piece behind and do that. It just happens naturally. And here it is happening naturally here. You see how exaggerated. Yeah, you get a spring runoff. It's going to cut and make a shortcut eventually across all of that and leave that remnant behind. So that's how, we've got a place nearby Baton Rouge called False River because it is a false river. So they call it that, but it's geologically, they're all false rivers or oxbow lakes. That's the term they use. However, with the Mississippi River, we have built this levee system, and we've stopped that process. So here in Baton Rouge, down by LSU, you've got these extreme bends that are going to be held there for probably 100 years until we probably can't fight it any longer, and eventually it'll still win. But the reality is the river, if we hadn't put the levee system in there, it probably, the experts say long ago, 50 years ago, it would have changed. And be running through the Atchafalaya Basin on its own, and it would have bypassed Baton Rouge and New Orleans altogether, and it would be dumping sediment where we needed it. So when you start looking out here at this big toe of Louisiana, we're dumping sediment where it is useless, where the Gulf is deep, and so it would take forever for it to make a real difference in building land. So when you start looking at, the pictures here on this picture, I'm going to zoom in on each one of them here. So let me zoom in on this thing. But the delta, we're building useless land that's going to take forever to turn into actual land because it's so deep out there. And meanwhile, we're losing shoreline between Baton Rouge and Lafayette down there. Between there, going all the way out to the Gulf, we're settling ground, and we're not replacing sediment. Not at a good enough rate anymore. So we're the ones that are the cause of us losing land. So you look at the top picture and the bottom picture, and you can see that we're going to have beachfront property on the journey from Baton Rouge to Lafayette at some point, because the Atchafalaya Basin is going to grow to become the Gulf over time here. So here we are currently, roughly, and by the time you get to 2021, I'll be long gone. But, it will have changed. But they'll still be partying in the French Quarter. But anyway, so this is the problem. It's not we got a combination of things. We're putting no new sediment back in there. So the lack of new sediment, plus the settlement of the existing soil continues. And then sea rise is, definitely happening at some rate. It's still a very small thing, but it is rising at some level. And all these things together collectively increase. So this is what we expect. Okay, so that's enough gloom and doom on that front. But, if I was in Homa, I would be a little concerned about this. Okay. One thing we do not have to worry about, the yellow part of this map is the good part. That ozone, radon. I'll get the right thing right here eventually. Let me get another sip of coffee. Radon gas is emitted in lots of places, especially where you see the red on this map. And those are generally mountainous areas, unweathered areas where there's natural uranium in the ground and there's radon that escapes. So it happens a lot all over the nation in places. It's the second leading cause of lung cancer in the nation. But you can see in Louisiana that has nothing to do with cancer in Louisiana. There's no radon. It's all heavily weathered material. So we don't have to worry about this. But if you did have to worry about it in other areas of the country, how do you deal with it? So here's the problem. It seeps into basements, into the buildings, but particularly a problem in basements because those are lower than everywhere else. And so the gas radon is heavier than air, so it tends to collect in basements. And so that's where it's the biggest problem. So here you have anybody sleeping in a basement or living in a basement. Now, if you have a basement that's open on one side because it's built into the hillside, you have less trouble with this because this stuff is pouring out through the doors and stuff. Less of a problem. But when you have an actual true basement that's lower than everything else, where you got to climb upstairs to get out of it, that's where the biggest problem is. So there's a couple of techniques they use because it's emitting in any cracks and finding its way from water. If you got a well water, it's collecting there and coming in all kinds of ways. So one way is to actually have free draining gravel underneath the slab, and then you suck like a vacuum on an ongoing, slow, steady, small little vacuum kind of action to suck up that radon and vent it outside and let it go around the neighborhood. Well, if it spreads outside, it'll disperse and it's not a problem. But radon is about 7.5 times heavier than air, that's why it tends to collect in the basements. Not a problem at all in Louisiana, even if you had a basement. So aggregate strength, you see, all things being equal, the left-hand pile is round rock, and there's just not going to be as much interlocking or friction between the particles the way there is with the right-hand pile where you've got angular material. So when you have a tire on the dirt, it would tend to have a cone-shaped surface that the weight of that tire, if you're standing still, is pushing out. So the particles down deeper in the ground are not under as much compression as they are at the top of the ground. So you need your best particles near the surface when you're building a road to make it strong. So when you start having a well-sorted mixture, you get more surface area. That increases the friction. So look at look at the right-hand side. I've got these 4 bullets here, and each one of those things could be turned into a test question in some fashion. So remember, each one of these are all important study guide points. They'll be in the study guide, and I'll ask questions about it in the quizzes. So you want to make sure you understand each of these points. So the first one, well-graded aggregate increases the strength of the aggregate. So well-sorted reduces the strength. So well-graded, you're going to have more strength, structural strength, because you've got more surface area to connect all these particles from large, medium, and small particles. So the second bullet says the larger the maximum aggregate size, that increases the strength. So having very large boulders in this mix helps. And that's true for even concrete mixes, as I mentioned earlier. So when you've got a very large, massive concrete pour, like for a hydroelectric dam, where they might have 60-foot, 100-foot thick walls of concrete, they're going to use huge rock size, and they're going to well grade it all the way down. And that gives them a lot more economical strength of concrete. Less cement needed for the mix. The third one down, the flat broken aggregate faces, the angular pieces, that increases the strength by the interlocking that you get in the aggregate mix, and that's true for the gravel mix. The very worst sand that you can use for a concrete mix would be desert sand, because literally the grains are blowing around on the sand in the desert, grinding against each other and making microscopically the individual sand particles very round. So they make a horrible concrete. So in some of the great deserts of the world in the Middle East, they have to haul angular sand in from somewhere else. And I'm sure there's somebody at the dock that's saying, oh my goodness, they've lost it. We got sand everywhere and they're shipping in sand. What the heck? If you don't know, and how could you if you can't see what that looks like under a microscope? So flat broken aggregate faces increases the strength by interlocking parts, like puzzle pieces. And then finally, the third or the fourth truism on this page, all 4 of them work together, and we use all of them to make a good structurally strong aggregate. Compaction. When you start compacting whatever you put down as a foundation underneath your building, underneath the roadbed, compaction increases the strength of the aggregate mass by the friction in interlocking that you get. It's like jamming the puzzle pieces together. Once they're all kind of jammed together, it makes it very dense. So that limestone road building mix, by the time you take this angular, well-graded mixture, fine, going from large, medium, and small, all the way down to the finest particles of limestone, of the lime mixture in the limestone mix, and then you compact it, it makes a very strong mix. It's actually hard to dig into it. It's kind of like a concrete, except that concrete would not get softer and be easier to dig through when it gets wet. Concrete is hard regardless of the water. In fact, in the long run, having moisture on the concrete makes the concrete stronger once you've got past the initial set. Anyways, let's get away from concrete. Okay, so this page is an important page. There's 4 possible test questions on this page, basically. Compaction, the definition, densification of the material resulting in an increase of weight per unit volume. So the pounds per cubic foot goes up when you compact. The aggregate unit stress is reduced at increasing depths. So the material should be arranged with the weaker, less expensive aggregates at greater depth. So when you're building a road, this is a truism there. So you want to put the very best, denser, stronger aggregates at the surface, and as you're building a road, you can have cheaper, weaker materials down below. So that's how it works. You can dig out 4 feet of ground and build a super highway on top of the ground, and you say, well, it's softer down below. Yes, but it can be, because the loads you're putting on the road distribute out like a cone further out from the road, and so that you can distribute that load over a larger area that way. So there's something called bank cubic yard material, or bank material, and then there's swell material, there's compacted material. So the bank cubic yards of material is where you get it from Mother Nature. So if you go and dig in your yard where nobody has been, well, in the city, sometimes your yard has been dug up in recent times, especially in a new subdivision. But if you were out into a new area that hadn't been untouched by humans ever, or at least as far as any common time at all, we would call that bank material, the way Mother Nature, undisturbed, put there the way Mother Nature put it. And we would call those bank cubic yards, the volume of that material, bank cubic yards of material. So that has a certain density, depending on what it is and all that. And then the swell material is where you're talking about loose material. When you dig the ground up, it takes up more volume as you dig it up. You dig it up, whether you're digging a grave or digging a hole for a foundation or whatever, the dirt that you dig out of there and put somewhere else is going to take up more volume than it did in the ground. So it swells up, you would say, if you haven't done. It's not like an infection or anything. It's like but we call it loose cubic yards. And so, the bank cubic yards, the abbreviation is BCY, bank cubic yards. The loose material we call loose cubic yards of material. And then if you go back to put that same dirt in the same hole carefully and collecting it all and putting it all back in there, and you compact it the way you have to in order to make it well compacted again, you actually can end up compacting it tighter than Mother Nature would have done so, because Mother Nature did it in a gradual, slow way and ended up with a structure with some air voids, but it still has well compacted. Compacted material will take even less volume than the bank material did. So it's a third different volume. And so we call that CCY for compacted cubic yards. So I'm not going to go through the math on this right now. I just want to introduce the concepts. But on the next page or two right here, I've got a thing that's showing you something. In a math problem, when we get to it, and we're only going to have a couple of these math problems on the actual exam, one or two. So it's not going to be a lot, but I'll have in my math quiz for exam 1, there is there'll be a few more than that in there just to give you the idea of this thing. But I will give you in the problem what the swell factor is, as far as how much the loose cubic yard conversion factor would be and how much the compaction cubic yard conversion factor will be. They will be given in the problem, and then you're just doing the little math problem with this to figure out how much you're going to be either adding or subtracting to the volume to convert from bank cubic yards to loose or bank cubic yards to compacted, that sort of thing. So that's the concept. We'll get into the math of it as a thing. I'll have a video dedicated to that too, that you can be using to really help play as many times as you want trying to understand it, and I'll have some problems that you can work on too. But anyways, here's the Hoover Dam, built during the Great Depression, 1931-36, and I've heard different numbers here about. These are the smallest numbers I've seen, where there's at least 4.4 million cubic yards of concrete in that thing, and it looks a lot prettier than that. This thing is when they were forming it, all building up the farms and stuff like that along the way. But again, back then, a lot of manual labor involved. Tremendous amount of labor, which they needed because the Great Depression, a lot of people were out of work, so it gave a lot of people meaningful work. A very important dam to this day, and here it is today in the background there. And just in recent times, in the last couple of decades, they built this wonderful bridge across there, modern feet. I've got a whole bunch of interesting information about that bridge that I can share too, for maybe an interesting stuff kind of category. I guess I should probably start in the course too, in case people want to go back to look at that. But that dam is still in use today. The only thing that's really changed that's just so dramatic is there's such a shortage of water that's needed for many states around the Hoover Dam, including California and Nevada and Utah and otherwise. The water level is way down in there, so they can't generate as much electricity as they used to. And they don't have as much water, therefore, for irrigation, farmland, and cities and everything else. It's a whole problem in that part of the country. It used to be everybody drove across that bridge, across that dam, and so it's only been recent times that they have this fancy freeway running past there in a way where you zip past there instead. That's enough. Call it a day.